So what we're going to talk about now is we're going to talk about something called Lagrange multipliers. And this is a way of utilizing partial derivatives or working with functions of multiple variables. And so let's take a look at an example here. What we're going to be doing is we're going to be doing some optimization, that is like working with our maximums and minimums. But what we're going to be doing then is we're going to be adding in what's called a constraint. A constraint being that this is something that we can't go above or below. And in order to add in those constraints when we're working with multivariable functions, we're going to be utilizing this method of Lagrange multipliers. So let's say, for example, I have Pro T Company has developed a profit model that depends on the max number X of golf balls sold per month and the number of hours per month of advertising Y according to this function. So Z equals f of xy equal to 48x plus 96y minus x squared minus 2xy minus 9y squared, where Z is measured in thousands of dollars. The maximum number of golf balls that can be produced and sold is 50,000, and the maximum number of hours of advertising that can be purchased is 25. Find the values of X and Y that maximize profit, and then find the maximum profit. So what we have here is we have a maximization problem, but what you'll notice is that we have a maximum number of golf balls being 50,000, so basically that X has to be less than or equal to 50,000, and the maximum number of hours of advertising that can be purchased is 25, meaning that Y, must be less than or equal to 25. These are two examples of what we call constraints, not restraints, but constraints. And what they do is that they actually provide us with information that will allow us to then go and solve our particular problem. All right, so what we're going to do is we're going to say, okay, well, what's the method that we're going to use in order to go about doing that? And that method here is called the Lagrange multipliers. So what this is an example of an optimization problem. So we have this optimization problem. You've seen them before in single variable calculus, but this method is actually quite different than the ones that you used in single variable. Inside of this optimization problem, we have something called our objective function. So f of xy equal to 48x plus 96y minus x squared minus 2xy minus 9y squared is called our objective function. X less than 50,000 and y less than or equal to 25, these are called our constraints. So as we're working, you want to make sure that you know, okay, that's what he's talking about when he talks about our objective function, and that's what he's talking about when he talks about our constraints. Now, if you think about this, so let's just look at this method of Lagrange multipliers, talk about it in terms of just having a single constraint. So suppose that we have two functions, f and g. They're functions of two variables with continuous partial derivatives at every point of some open set, containing the smooth curve g of xy equal to 0. And suppose that f, when restricted to points on the curve g of xy equals 0, has a local extremum at the point x naught y naught, and that delta, or that the gradient of g of x naught y naught is not equal to 0. Then there is a number lambda called a Lagrange multiplier for which the gradient of f at x naught y naught equals lambda times the gradient of g at x naught y naught. So we've got a couple of things here. We want to kind of notice, so f is going to be our objective function. G is going to be our constraint. And then we've got lambda. Lambda is going to end up being our Lagrange multiplier. Okay? And that's what that's called, the Lagrange multiplier. It's also called lambda. That's the name of that thing. Okay? What we can see here is basically we're going to do this kind of thing. We're going to find a local extremum for f on the smooth curve, or using the constraint. Okay, so we're going to figure out what our local extremum is for at a particular point. All right, and then we're going to go out and we're going to find our gradients for both f and g. Right, plug in that extremum and then figure out what lambda is. Okay, and we'll utilize that information in order to kind of help us solve what's going to end up becoming a system. Now let's look at what happens when we have problems with two constraints. So suppose that we have a problem that has two or more constraints. We're going to need to have two or more Lagrange multipliers to solve our system. And as the constraints of the functions get more complex, we often have to resort to using linear algebra to solve these systems. we're going to restrict ourselves to systems with 2 Lagrange multipliers, and that way we're only really going to be looking at like 3x3 systems, or systems that are not too difficult or too calculationally intensive for right now, at least for our examples. So let's suppose that what we want to do is we want to find the extreme values of the function for f of x, y, z equals x squared plus y squared plus z squared. And we're going to be subject to the constraints z squared equals x squared plus y squared, and x plus y minus z plus 1 is going to equal 0. So what this is going to look like then is we're actually going to need to be, our method of Lagrange multipliers is going to have that the gradient of f is going to equal lambda 1, our first Lagrange multiplier, times the gradient with respect to g, plus the second Lagrange multiplier, a different Lagrange multiplier, times the gradient with respect to h. Okay? And we would actually do that for every single constraint that we possibly have. And so what it does is that it actually expands the system of equations that you're working with. So we're going to set this up. We're going to have g of x, y, z then. All right? This is going to be our first function. It's going to equal x squared plus y squared minus z squared. And then we'll have h of x, y, z equal to x plus y minus z plus 1. So now those are constraint functions. We'll find the gradient with respect to f. So the gradient with respect to f is going to end up being 2x, 2y, 2z, like we had before. The gradient with respect to g is going to equal 2x, 2y, negative 2z. And the gradient with respect to h is going to end up equaling 1, 1, negative 1. Now what we'll need to do is to set up our system of equations utilizing this particular function right here. So I'm going to set it up for an x, a y, and a z. So 2x is going to equal lambda 1 times 2x, or we'll just write it times 2x, plus 1 times lambda 2. 2y is going to equal lambda 1 times 2y plus lambda 2. And 2z then is going to equal lambda 1 times negative 2z plus or minus lambda 2. So what we have here, and then we have our two constraints. Our two constraints, we're going to have x squared plus y squared minus z squared equals 0, and x plus y minus z plus 1 equals 0. All right? So if we look here, we've got x, y, z, lambda 1, and lambda 2. And if you remember how we go about solving systems of equations, if I've got 5 variables, I'm going to need 5 equations. But that's exactly what I've got here. So what I'm going to do now is I'm going to go out and solve for lambda 1 and lambda 2 so that I can get each one of my variables in terms of the other variables. Okay? So let's start out with... So what we're going to do now, as I said before, is we're going to solve for lambda 1 and lambda 2. Let's actually use this third one right here. Okay? And let's get that 2z is going to equal negative 2 lambda 1z minus lambda 2. And we'll solve for lambda 2. So this is going to give me 2z minus 2 lambda 1z equals negative lambda 2, or excuse me, plus 2 lambda 2. Divide by, make it negative. This now makes me negative 2z minus 2 lambda 1z equals lambda 2. Okay, so now we have lambda 2. And what we can do now is we're going to substitute that into both of these equations. And let's do that. We're going to do this kind of to the side. So that's going to give me then 2x equals 2x lambda 1 plus, or rather minus, 2z minus 2 lambda 1z. And then we have that 2y is going to equal 2y lambda 1 minus 2z minus 2 lambda 1z. Right? So now what we can do is we can actually solve both of these, solve both for lambda 1. So we solve for lambda 2 first, and now we're going to solve for lambda 1. Do you have to do it in that order? No, you don't, but let's do it this way, see what happens. So we'll divide through by 2. This then gives me that x, for the first one, divide through by, or multiply by 1/2. Okay, we're actually going to do that for both. we're going to get then that x equals lambda 1x minus lambda 1z minus z, and y is going to equal lambda 1y minus z minus lambda 1z minus z. Okay? Add over, let's look at them each one at a time. We're going to add z to both sides. X plus z is then going to equal lambda 1. I'm going to factor that out to lambda 1 times x minus z. And so lambda 1 is going to equal x plus z over x minus z. And in my second equation, I'm going to get y plus z is going to equal lambda 1 times y minus z. So that means that lambda 1 is going to equal y plus z divided by y minus z. It's at times like these that I wish for a whiteboard because of the amount of work that actually has to get done here. So we've got both of those. We've actually figured out what lambda 1 is. That's good. Good news. So lambda 1, we've now got that y plus z divided by y minus z is equal to x plus z divided by x minus z. Now we're going to do some algebra. All right, so this is just algebra. We'll cross multiply. So that's y plus z times x minus z equals x plus z times y minus z. This gives me now xy plus xz plus xy plus xz minus zy, or y minus yz minus z squared. And that'll equal then xy plus yz minus xz minus z squared. We're now going to set everything equal to 0. Okay, again, just some algebra here. So kind of follow along. Right? Okay, we're going to set everything equal to 0 so we can do this work. We're also, so the z squareds are going to end up canceling out. We also have a minus xz, we have a plus xz, so that's going to end up being 2xz. We'll have our xy's are going to cancel out, and our yz's are now going to become 2 minus yz's. So add xz, subtract yz from both sides. I get 2xz minus 2yz equals 0. Okay? Now we can factor out z. So z times, and we get 2x minus, or let's just actually make it 2z times x minus y equals 0. And that actually gives me a value here now. Kind of simplifies things. That means that z equals 0 or x minus y equals 0 by the zero product property. Remember your algebra there? So z equals 0. Hey, great. I figured out what z is. And then we have that x has to equal y. So x has to equal y. And that's great. Now what I can do then is I can plug that back into, say, my constraint equation, like x plus y minus z plus 1 equals 0. What we have to have now is we actually have to have that both of these things satisfy these constraints. So that means that x squared plus y squared has to equal z squared. Right? That was one of our constraints. And then we also had that x plus y minus z plus 1 has to equal 0. Okay? Well, if z equals 0, then we get that x squared plus y squared is going to equal 0 squared. And that means that x squared plus y squared is going to equal 0. So x would have to equal 0 and y has to equal 0. That's the only way to actually solve that. The problem is that actually doesn't satisfy the second constraint. If I let x equal 0, y equals 0, and z equals 0, then 1 equals 0. Okay, we can just see that. 0 plus 0 minus 0 plus 1 does not equal 0. So it does not satisfy the second constraint. So what do we have to do? since using z equals 0 doesn't satisfy the second constraint, we can't actually use z equals 0 as a solution. We've got to get rid of it. So no z equals 0. We can use, though, x equals y. So we're going to do that. So what we're going to do is we're going to say, okay, well, then x squared plus x squared is going to equal z squared. So we use the first constraint. And then our second constraint, right, is going to be then x plus x minus z plus 1 will equal 0. What that gives me then is that that's going to give me that 2x squared equals z squared. And it'll give me that 2x is going to equal, or 2x plus 1 will then equal z. So we'll just move the z over to the other side. And then that way what we can do is that'll allow us to just substitute in z. So now 2x squared is going to equal 2x plus 1 squared. So 2x squared equals 4x squared plus 4x plus 2. We'll subtract over the 2x squared to both sides. And that then gives me that 0 equals 2x squared plus 4x plus 1. Oh, excuse me, that should be a 1. It should be a plus 1, excuse me. So this should be plus 1. And now we'll just use quadratic to find x. So x is going to equal negative 4 plus or minus the square root of 4 squared minus 4 times 2 times 1, all divided by 2 times 2. This thus is going to be negative 4 plus or minus the square root, and this is going to be 16 minus 8. So that's going to be square root of 8 divided by 4. We can pull out, we can make this negative 4 plus or minus 2 root 2 over 2. So x could either equal negative 4 plus, or negative 2 plus root 2 over 2, or x could equal negative 2 minus root 2 over 2. And those are two options that we have for x. Since x equals y, y then would have to either equal negative 2 plus root 2 over 2 when x is equal to that, or y would equal negative 2 minus root 2 over 2. Right? So this is our grouping thus far. And now all I really need, or all I really need, is to just go in and figure out what value then satisfies my last set of constraints. Okay? So let's take then, let's plug it into this x squared plus y squared equals z squared. Excuse me. X squared plus y squared equals z squared. So actually, probably better for us to just use x plus y minus z plus 1. So we'll have x plus y. So x and y are both the same. So we'll get negative 2 plus root 2 over 2 plus negative 2 plus root 2 over 2 minus z plus 1 equals 0. So if we pull the z over to the other side, we're going to get that z equals, and so this is going to end up being negative 4 plus 2 root 2 over 2 plus 1 equals z, right? Because we'll just add the negative 2's, add the root 2's. So this then is just going to be negative 2 plus root 2 plus 1, which is just equal to negative 1 plus root 2, and that equals z. All right, so that's our first triple. Our first triple is going to end up being negative 2, it's going to be negative 2 plus root 2 over 2, comma, negative 2 plus root 2 over 2, and negative 1 plus root 2. Our second triple, now, using the same constraint, we'll plug in, we got negative 2 minus root 2 over 2, plus negative 2 minus root 2 over 2, plus 1, right? And then we'll let that equal z. Just like we did down here, Okay, utilizing that, we're just moving the z over to the other side. So this gives me negative 4 minus 2 root 2 over 2 plus 1 equals z. So we get negative 2 minus 2 root 2 plus 1 equals z. So this is now negative 1 minus 2 root 2 equals z. And that gives me my second triple. And my second triple is negative 2, or negative 1 minus 2 root 2, or excuse me, x is negative 2 minus root 2 over 2, y is negative 2 minus root 2 over 2, and then we have negative 1 minus 2 root 2, and that is my second triple. Now what we'll do is we'll substitute it into f to find the minimum and maximum values. If we take our first triple, let's say f of, and we'll call this, we'll first take f of negative 2 plus root 2 over 2, negative 2 plus root 2 over 2, and negative 1 plus root 2. Plug it back into our constraint, and what we end up with is we end up with the value 6 plus 4 root 2. Okay? If I take now f of negative 2 minus root 2 over 2, negative 2 minus root 2 over 2, and negative 1 minus, and it should be minus root 2, not 2 root 2, minus root 2, what we end up with is 6 minus 4 root 2. Okay? This is clearly a local and these are our local extrema, subject to the constraints. You can see that actually this process is a bit more involved. Okay, we've got five equations, so constructing a system of equations with 5 equations can sometimes be very time consuming. So you basically, you have to kind of really be good at the setup and whatnot. In addition to kind of being able to move through the process pretty quickly if you're actually having to do some of this stuff by hand. Just notice that what we do first inside of it, whenever we're doing Lagrange multipliers, if we just want to kind of set this up first from the standpoint of solving the system, we'll solve for lambda I first. For each lambda I, so that's lambda 1, lambda 2, etc. Okay? Then we're going to substitute into the equations, to get x, y, z, etc. Right? Then what we have to do is we have to make sure that our solutions solve both constraints. So you do have to check that. Make sure that the solutions solve both constraints. If they don't, then you can't use that as a solution. It doesn't work. All right, so that's actually a really important thing. All right, so, and then afterwards, right, okay, then we plug back in, and then finally we've got to solve for f at our local, values for either x naught, y naught, or x naught, y naught, z naught. All right, and so that kind of finishes out what we were doing here for Lagrange multipliers. The process, right, is just very detail oriented. So you actually want to get used to becoming more detail oriented inside of your work, okay? Because it really is, it's a very basic premise, right? We're going to take the gradient, okay? The gradient of f equals, call it the lambda times the gradient of g, all right? And we're going to use that fact, or we're going to use the gradient of f equals lambda 1 times the gradient of g, plus lambda 2 times the gradient of f, or gradient of h, right? Basically, that's it. That's all you got to really think about. So consequently, not a lot of thought stuff, really a lot of process things.